we've done the order analysis for these sorts that we've written, and we have kind of talked in somewhat hand-wavy ways about how fast they are, saying that some things would be faster than others. But if you really want to know how fast something runs, if you have an application that is performance critical, you have to actually do performance testing. And that means that you have to time how long it takes for things to happen on the computer that you're going to be running stuff on. So I want to add the ability to do some performance tests to the sorts that we've already written. To do this, I'm going to write a function that I'll call timefunc. And I'm writing this because I want to test all of the different sorts that we've done. And doing each one, I could write the code for time testing 1 and then copy it and paste it and copy it and paste it. Yeah, we don't like to do that. It's much better if we can put it all in one place. Now, in order to make that work, the sort function, whether it's bubble sort or selection sort or insertion sort or a shell sort, has to be passed in. And this is something of type array of double goes to unit. That's the signature for all of our sorting functions. So whether it's the shell sort, takes in an array of double, gives back a unit, or the insertion sort, bubble, and min sort are the same. So we're going to pass in that, and we're also going to pass in the array that we want to do the time testing on. And part of the reason for this is if you want to have valid comparisons between sorts, you really have to make sure that you're sorting the same thing, because otherwise you might be giving kind of an unfair advantage to one sort over another. Okay, so I have this array. I don't want to sort the original, I want to make a copy of it. So to make a copy, in the book I use tabulate to make a copy. You can also use map. So we're going to map, and we're going to take each value and map it to itself. So we get back a copy of that same array. And now I need to kind of figure out what time it is, because in order to get a time for how long the sort takes, we have to take a difference. So I'm going to make a variable called start, and there is a function called system.nanotime, and that gives you back a measure of time measured in nanoseconds, which is why it's called nanotime. And as a baseline, you don't really know what the baseline is, but you know that if you have two of these and you take the difference, it tells you how much time passed between one of them and the other. So after we've done that, we can sort our copy, and then let's go ahead and let's get an end value. And actually, I'm going to make this return a double, which will be how long it took in nanoseconds. Or sorry, in seconds, not nanoseconds. I don't really want to work in nanoseconds. Seconds make a lot more sense to me. So that would be end minus start divided by 1e9, because there are 10 to the 9 nanoseconds in a second. Okay. Now that we have that, we can make our array up here. I'm actually going to get rid of those, and we're going to make this bigger. 10,000, how about 100,000 elements? That should be long enough that it takes a while. So print line bubble sort, and we will call timefunc. We'll pass it bubble sort and our array. And remember, the timefunc makes a copy of it, so it won't alter that array. We also, in this file, have a min sort, an insertion sort, and a shell sort. So we'll change these so they call the appropriate ones. Let's see if I've typed that all in correctly. We'll also find out if 100,000 was a good number to pick, or if I went a little bit longer than we want to wait in a video. Probably should have started with 10,000 and then worked my way up. Yeah, let's start with 10,000. We'll see how long that takes. Remember, these are order n squared sorts with the exception of the shell sort. So 100,000 is 10 to the 5. So that means that when we order n squared, is doing on the order of 10 to the 10 operations. Okay, so, and of course that factor of 10 should have sped this up, because these are order n squared, really should have sped them up by a factor of 100. So if these take 0.2 seconds with 10,000, we would have expected them to take 20 seconds each with 100,000. I don't really want to wait 20 seconds each, but it might be nice to get these up to the level of about 1 second each. So let's see, that would mean I need it to take 4 times longer to run. We'll go a little bit longer than that. We'll make it take roughly 9 times longer. Okay. Let's run it again. You'll note the numbers are different. So 1.7 versus 1.9, 0.77, 0.80, 0.138, 0.155, 007, 065. You're not going to get the exact same results. Part of that is the arrays are different numbers each time, even though all of these use the same array and all of these use the same array. But it also just, there are other things that happen to be running on the computer that I'm on. There are various factors that can cause performance to vary. So when you're actually measuring performance, one of the other things you have to do is you have to run it several times and take the average of all of those outputs. Clearly though, from these runs you can tell bubble sort is definitely the slowest, the selection sort is faster, and it looks like on average it's faster by about a factor of 2, because apparently the less swapping is helping it out here. Though insertion sort is beating both of them quite handily by more than a factor of 2. Part of that is the way that I write the insertion sort. I do not do full swaps. You can write insertion sort where instead of, you don't have this line and this is a full swap. But if that's a full swap, it's doing the work of a full swap. Not doing a full swap can actually give you an additional speed benefit, and as we would expect, shell sort clobbers all the others, and it will, the lead that shell sort will get even larger as we make our array bigger. If we did this for 100,000 or, heaven forbid, 1,000,000, we'd be sitting here for a while, at least for these other sorts, but the shell sort would have a tremendous lead on them by that point.